In this problem, we're going to find the minimum value of log base 2 of x plus log base x of 2, where x is greater than 0 and x is not equal to 1. First thing I'm going to do is simplify this using a substitution. The key insight is to use the change of base formula. Remember that log base x of 2 can be written as 1 divided by log base 2 of x. So let me make a substitution to make this cleaner. We can let y equals to log base 2 of x so I'm letting y equal log base 2 of x, then log base x of 2 by the change of base formula equals to 1 over log base 2 of x. Basically, we have log base x of 2 equals to 1 over log base 2 of x, which equals to 1 over y. So our full function becomes y plus 1 over y, which is much simpler. Then we have f of x equals to y plus 1 over y. So now, what values can y take? Well, x is greater than 0 and x is not equal to 1. That means log base 2 of x can be any real number except 0. Basically, since x is greater than 0 and x is not equal to 1, we'll have y belongs to real numbers except for 0. Now, let's find the minimum using the AMGM inequality. But here's the first trap you need to avoid. The AMGM inequality only works when the numbers are positive. So we need to split this into two cases based on whether y is positive or negative. We can start with case 1 where y is greater than 0. So first case, y is greater than 0. So basically we'll have x greater than 1. By AMGM equality, when y is positive, both y and 1 over y are positive numbers. So we can apply AMGM. The AMGM inequality says that the arithmetic mean is greater than or equal to the geometric mean. So y plus 1 over y divided by 2 is greater than or equal to the square root of y times 1 over y. In math language will become y plus 1 over y divided by 2 is greater than or equal to square root of y times 1 over y. So the square root of y times 1 over y is just the square root of 1, which equals to 1. Now we can multiply both sides by 2. So then we'll have y plus 1 over y is greater than or equal to 2. Now when does equality happen? AMGM equality occurs when all the terms are equal. So we need y equal to 1 over y. That means y squared equals to 1 because we multiply y on both sides. And since we're in a case where y is positive, you'll have y equals to 1. If y equals to 1, that means log base 2 of x equals to 1, which means that we'll have x equals 2 2. To verify when x equals to 2, we get log base 2 of 2, which is 1, plus log base 2 of 2, which is also 1. So the value is 1 plus 1, which equals to 2. So in the positive case, the minimum is 2. And then we're going to do case 2, where y is less than 0. Which means that 0 is less than x is less than 1. We can let y equals to negative t, where t is greater than 0. Then our function becomes negative t plus 1 over negative t. That's negative t minus 1 over t. So negative t minus 1 over t is going to equal to negative t plus 1 over t. Now t is positive, so t and 1 over t are both positive. We can apply AMGM to them. By AMGM, t plus 1 over t is greater than or equal to 2. So, by AMGM, t plus 1 over t is greater than or equal to 2. So negative times the quantity t plus 1 over t is less than or equal to negative 2, meaning that when y is negative, our function is at most negative 2. Equals to negative 2 when t equals to 1, which means y equals to negative 1, which means that x equals to 1 over 2. So max is negative 2 when t equals to 1. Which will mean that y equals to negative 1, x equals to 1/2. But wait, this is a maximum, not a minimum. As x gets closer to 0, y goes to negative infinity, and the function goes to negative infinity. As x approaches 1 from below, y approaches 0 from the left, and the function also goes to negative infinity because of that 1 over y term. So in a negative case, there is no minimum. The function goes down to negative infinity. So, we can say that function f of x approaches negative infinity as x approaches 0 from the right side or x approaches 1 from the left side. Then, we can verify the answers in calculus. We have the function g of y equals to y plus 1 over y, where y is not equal to 0. We can take the derivative with respect to y. So here we can write g of y is equal to y plus 1 over y, which means that g prime of y is equal to 1 minus 1 over y squared. The derivative of y is 1. The derivative of 1 over y is negative 1 over y squared. So g prime of y equals to 1 minus 1 over y squared. We can set the derivative equal to 0 to find critical points. So 1 minus 1 over y squared equals to 0, which will mean that y equals to plus minus 1. This gives us y equals to 1 or y equals to negative 1. Now let's check the second derivative to determine if these are maxima or minima. The second derivative says of g is 2 over y cubed. So g prime prime of y equals to 2 over y cubed At y equals to 1, g double prime of 1 equals to 2 over 1 cubed, which is 2. Since this is positive, y equals to 1 is a local minimum by the second derivative test. So g prime prime of 1 equals to 2 greater than or 0, that's a local minimum. The value of this minimum is g of 1 equals to 1 plus 1 over 1, which is 2. At y equals to negative 1, g double prime of negative 1 equals to 2 over negative 1 cubed. So we have g prime prime of negative 1 equals to negative 2 is less than 0. That's a local max. Then we have g of negative 1 equals to negative 2. This confirms what we found is AMGM. The function has a minimum of 2 when y equals to 1, which corresponds to x equals to 2. So our final answer is the minimum value is 2. And it occurs when x equals to 2. So that is how you're going to solve this problem.